So today we are going to continue our knowledge of exponents. Now we covered exponents in an earlier lesson, section 1.3, if you recall. But today we're going to add to that knowledge specifically with negative exponents. So if you recall, an exponent is simply relating the number of times a digit is being used as one of the factors. My example that I used earlier was 5 cubed, where it's 5 times 5 times 5. So the 5 is known as the base, and it tells me what number is being used as a factor. And then the number on top is known as the exponent or the power, which tells me how many times I am using my base as a particular factor. So in this particular case, we have 5 cubed, so that means I'm using 5 as a factor 3 separate times. Now that we covered earlier, but now let's talk about what happens when we go into the negative values for my exponent. Let's take a look at an example. Let's say I had 5 to the 4th power. Of course, that's 5 times 5 times 5 times 5, which would give me 625. But let's just say, for instance, that I were to divide that by a value of 5, the value of whatever my base is. Well, that would make it only 125, or 5 cubed. So in the process of dividing by my base, I could cancel out one of my numbers in the numerator, which would reduce my exponent by one value. If I do that again, if I take that 5 cubed and I divide by another 5, well, that's going to drop my exponent down to a 2. So now I'd get 5 squared. If I did it again, then it would drop down to 5 to the 1st power. So every time we divide by our base number, we are decreasing our exponent by a value of 1. So now I'm at 5 to just the 1st power. If I were to divide by 5 again, well, 5 divided by 5, of course, is 1. But what does that look like in an exponent? That'd be 5 to the 1 minus 1 power, or 5 to the 0 power. So that shows us that 5 to the 0 power would equal to 1, when in fact anything to the 0 power is going to be equal to 1. A negative 2 to the 0 power, if I had it all in parentheses, would also equal 1. So anything to the 0 power is going to be equal to 1. If I were to divide that by 5 again, I would have 1 divided by 5, or 1/5. Well, in my exponent notation, that would be 5 to the 0 minus 1 power, which would be 5 to the negative 1st power. So here's what that means. If you have a negative exponent, it's indicating that your base is in the wrong position. Rather than being in the numerator, it should come down to the denominator and become a positive exponent. Or if it's already in the denominator with a negative exponent, you can move it up to the numerator and change it to a positive exponent. Here's my example. 5 to the negative 3 I could rewrite as 1 over 5 cubed. And of course 5 cubed is 125, and we could simplify that out. But it would be 5 cubed in my denominator. So I move it to the other location and I change the value of my exponent to the opposite sign. So what was negative becomes positive, or if I moved it from a positive position down, then I would make my exponent a negative. So here's another example. 2 to the negative 13th would be the same as writing 1 over 2 to the 13th power. You could check this on a calculator. If you took, for instance, 1 divided by 5 cubed and saw what the numerical value of as a decimal was, and then you took 5 to the negative 3 power on your calculator and hit equals, it would give you the same decimal answer. So therefore they are indeed equivalent. Once again, whenever an exponent is equal to 0, we are going to say that that value is a positive 1. Now I do want to show you one thing. If we had negative 5 to the 0 power, that would be equal to negative 1, because the 0 is only on the 5. If I were to write it as a parentheses of negative 5, and outside the parentheses I put the 0, now it's saying my entire base, which is everything inside the parentheses, because the exponent is outside of it, Everything inside the parentheses is to the 0 power. Anything to the 0 power would be equal to a positive 1. So you do want to be careful as you're looking at questions that have a 0 exponent. Where is that negative sign? If it is included with the exponent, then the answer is going to be a positive 1. If it's not included with the exponent, then your answer is going to be the negative if it's preceded by a negative sign. Let's try to evaluate some of the following. Take a moment and do 3 to the 5th power. Now, that was a throwback from section 1.3. 3 to the 5th power, of course, is 3 times 3 times 3 times 3 times 3, which should give you 243. Now let's try 6 to the 4th power. Well, that's going to give me 6 times 6 times 6 times 6. On a calculator, if you did that, you should get 1,296 as your answer. What about 8 to the 0 power? Well, as was mentioned before, anything to the 0 power is going to be 1. So your final answer is indeed 1. What about 9 to the negative 2 power? Nine to the negative 2 would be the same as writing 1 over 9 squared. And since 9 squared is 81, we have 1 over 81. Go ahead and leave them as fractions unless it says otherwise. Now that brings us to working out problems with exponents that are a little bit more of a challenge than just simply values that I can raise. There are 3 basic rules that we're going to look at when using exponents with other exponents. And we're going to start off with what is known as the product rule. The product is the answer to a multiplication problem. If I have 2 bases that are exactly the same, I'm multiplying those bases together. What I'm going to do with the exponents is I'm going to add those exponents. Here's an example of 5 cubed times 5 to the 5th. That gives me 5 to the 3 plus 5 power, which of course is 5 to the 8. Now, here's a reason why it is this way. Let's take it in the long form. So 5 cubed would be 5 times 5 times 5. 5 to the 5th would be 5 times 5 times 5 times 5 times 5. Well, if I were to write all of these out, since I'm multiplying, I really don't need this set of parentheses here. I can just put a multiplication symbol in between. And if I were to have just this as a list of numbers and say, write that as an exponent, what would you come up with? You'd come 5, which are our base. 1, 2, 3, 4, 5, 6, 7, 8. You would tell me that that is equal to 5 to the 8th power. And you would indeed be correct. So this is why the product rule works. Now let's try one with negative exponents. In this particular case, I've got 2 to the negative 13th times 2 to the positive 5th. Now we cannot drop the negative sign, so we got to keep that in there. So that's going to give me 2 to the negative 13 plus 5 power, which in this case is 2 to the negative 8th. If I want to write that as a positive exponent, since it is a negative exponent, I need to bring it down to the denominator like we just learned, and that would give me 1 over 2 to the positive 8th power. Now let's try the quotient rule. The quotient is the answer to a division problem. And so since division and multiplication are opposite processes, we are going to, instead adding, we're going to subtract. So my quotient rule says that when I'm dividing like bases, I'm going to subtract their exponents. So here's my example. 5 to the 5th divided by 5 cubed would give me 5 to the 5 minus 3 power, or simply 5 squared as an exponent. And the reason for that, if I take 5 to the 5th and I write it out long form, and then I divide by 5 cubed, I can start canceling. These 5s cancel, these 5 cancels, these 5 cancels, leaving me with just 5 times 5, or 5 squared. So that's why the quotient rule works. Let's try a second one. Let's say I had 2 to the negative 13th divided by 2 to the 5th. Well, that would give me 2 to the negative 13 minus 5 power, or 2 to the negative 18th. If I wanted to write that as a positive exponent, then that would be 1 over 2 to the positive 18th power. As yet a third example, let's say I had 8 to the negative 5th divided by 8 to the negative 9th. Now keep in mind that I do have negatives and I am subtracting. So we got to go back to how we add and subtract negative numbers. So this would be the same as saying 8 to the negative 5th minus negative 9 power. Since I'm subtracting a negative 9, that would be the same as adding a positive 9, giving me 8 to the negative 5th plus 9, or simply 8 to the 4th. If you need help adding the sign numbers, then I would encourage you to go ahead and visit that lesson once again and maybe look over that information to help you out. And that brings us to the third and final rule that we're going to be learning today, and that is the power rule. The power rule is if I have an exponent on an exponent. So an example here of 5 cubed raised to the 5th power. Well, what is that going to actually accomplish? I'm going to multiply the two exponents together in this case, and here's the reason why. If I had 5 cubed and I were to take it to the 5th power, then that means I'm multiplying by another 5 cubed, and then another 5 cubed, and then another 5 cubed, and then a final 5 cubed, because I've got to take it to the 5th power in this case. Well, now I can use my product rule and I can add all those exponents together. So that would give me 5 to the 3 plus 3 plus 3 plus 3 plus 3 power, or 5 to the 15th. So it's much faster just to go ahead and multiply. So exponents on exponents, you are going to multiply. That includes if you have a negative exponent, such as this one. We have 2 to the negative 13th raised to the 5th power. Well, I can shortcut myself and do 2 to the negative 13 times 5. 13 times 5 is 65, so that'd be a negative 65. 2 to the negative 65th. And again, if I wanted to write it as a positive exponent, that'd be 1 over 2 to the 65th power. Let's see if you can simplify these, and I would like the answers as positive exponents. So do not change them to decimals. If they are a negative exponent, you need to change them to some sort of fractional form. Let's start off with 4 squared to the negative 12th power. 4 squared to the negative 12th power is going to be 4 to the negative 24th power. As a positive exponent, it's going to be 1 over 4 to the 24th power. How about 7 cubed to the 5th? Once again, I'm going to be using my power property here. I have 3 times 5, which gives me 15, so that gives me 7 to the 15th power. What about 10 to the 5th raised to the 7th power? Again, I'm using my power property. I have 5 times 7, which is 35, so I have 10 to the 35th power. 6 to the negative 5th to the negative 8th power. Again, I'm using my power property. I got a negative times a negative, which is going to give me a positive value. Since my base is 6, it stays as a 6. A negative 5 times negative 8 gives me a positive 40, so I have 6 to the 40th power. So 3 times negative 7, using my power property, would give me negative 21. So I have 9 to the negative 21st power. Since it is a negative exponent, I'm going to convert that to a positive exponent by bringing it down into the denominator. Give me 1 over 9 to the 21st power. How about one that's a little bit more of a challenge? We've got 5 squared times 3 cubed raised to the 4th power. Here we only have the 3 cubed that is being raised to the 4th power. It is not going to impact the 5 squared. So the 5 squared stays a 5 squared, but this 3 cubed raised to the 4th power is going to become 3 to the 12th. And since I asked to leave them as exponent form, that would be your final answer. Obviously, if we were to work that out on a calculator, we would get an actual number. How about 6 to the 4th raised to the 3rd power times 4 to the 4th raised to the 8th power? In this case, 6 to the 4th raised to the 3rd power is going to give you 6 to the 12th power, because 4 times 3 is 12. 4 to the 4 times 8 power, which gives you 4 to the 32nd power. So my final answer is 6 to the 12th, 4 to the 32nd. What about 7 cubed times 7 to the 5th? This is not using the power property. This is going to be using the product property. We have like bases, so we're going to add their exponents. And since 3 plus 5 is 8, I'm going to get 7 to the 8th power. 10 to the 5th times 10 to the negative 7th. Once again, these are like bases, so I'm going to add their exponents. I have 5 plus a negative 7. That gives me 5 to the negative 2 power. Now, according to the instructions, I wanted positive exponents. This is a negative exponent. So that tells me I need to move my 10 down to the denominator and change its exponent to be positive. So that is going to make it 1 over 10 squared. How about 9 cubed divided by 9 to the negative 7th? Now I'm using my quotient property. So I have 9 cubed as my numerator, 9 to the negative 7th as my denominator. So since I'm dividing, I'm going to subtract their exponents. So that would give me 9 to the 3 minus a negative 7 power, or 3 plus 7 power, which would give me 9 to the 10th. Now, as an alternative, you could convert this into something else. So for instance, if I had 9 cubed divided by 9 to the negative 7th power, because I'm dividing by that base, I could go ahead and move this base up into the exponent position, or up into the numerator position. That would give me 9 cubed times 9 to the positive 7th. Because I moved it up into the numerator, I had to change the exponent to be the opposite sign, which is now a positive exponent. I can use my product property and I can do the addition. So it would be 9 to the 3 plus 7 power, which still gives me 9 to the 10th. So if it's easier for you to think of it that way, you may go ahead and do that. But it is faster just to go ahead and do the subtraction of a negative if you're very comfortable with doing those kind of things. Let's try 5 squared divided by 5 cubed to the 4th power. Well, I'm going to go ahead and do my exponents first. So I have 5 squared divided by 5 to the 12th power. And since I'm dividing, I'm going to subtract their exponents. So that gives me 5 to the 2 minus 12 power, which is going to give me 5 to the negative 10 power. Since I'm supposed to write them as positive exponents, that's going to make it 1 over 5 to the positive 10th power. How about this one? 5 cubed, 7 cubed times 5 to the 8th to the negative 5th power. So I'm going to do this 5 to the 8th to the negative 5th power first. I have my power property that I'm going to use there. So that gives me 8 times negative 5, which is negative 40. So that gives me 7 cubed, 5 to the negative 40th. I've got to convert that into positive exponents. And so my 7 already has a positive exponent on it. It's a 3. So that's going to stay in my numerator. I don't need to move that. It's already got a positive exponent. If I moved it down to the denominator like I am going to do with a 5, then it would become a negative exponent. But according to my instructions, positive exponents. So the 7 cubed stays in the numerator. The 5 with the negative 40 exponent needs to move down to the denominator and become a positive exponent. So I have 7 cubed over 5 to the 40th power. How about 2 cubed to the negative 2 times 11 fourth to the 5th? Well, 3 times negative 2 gives me a negative 6, so I have 2 to the negative 6th power there. And 4 times 5 gives me 20, so that gives me 11 to the 20th power. Once again, I've only got one of my values that is a negative exponent, so that's the only one that needs to move. The ones that are positive stay where they are. So I've got 11 to the 20th up in my numerator, but I do need to move the 2 to the negative 6th down to the denominator, and so that gives me 11 to the 20th over 2 to the 6th. So today what we learned are negative exponents. When you have a negative exponent, that means it's in the wrong position. If it's in the numerator, we need to move it down to the denominator and change it to a positive exponent. If it's already in the denominator and has a negative exponent, that means we need to move it up to the numerator and change its exponent to a positive. Then we looked at 3 rules for using when you're multiplying like bases. If you have 2 like bases with exponents, you're going to add those exponents. If you are dividing like bases, you are going to subtract their exponents. And if you have an exponent on a number already with an exponent, you are going to multiply those exponents using the power property.